We have met gravitational potential energy, and we're now going to talk about a second type of potential energy, which is elastic potential energy. Now, one thing to note is we call it elastic potential energy, and you might think of pants or rubber bands, but really we're going to be talking about springs. So remember, anytime with potential energy, we have to make sure that the entire interaction is within our system. So the situation where you can define a spring or an elastic potential energy is when you include the spring within your system and whatever the other end of that spring is attached to. So that is now part of our system. Now this is obviously different than gravitational potential energy. It doesn't depend on height, it doesn't depend on mass, it doesn't depend on g. It also has different notation. We are still using capital U because it is a potential energy, but now we use subscript SP to stand for spring. What our spring potential energy does depend, there's still a 1/2, and now we have K. Remember, this is lowercase k, and that's our spring constant that describes the spring. The delta S is then the displacement from equilibrium. So we met this when we talked about spring forces. The spring itself has an equilibrium length, and then the potential energy is going to depend on how far the spring has been compressed or stretched from that. Note that we are then squaring it. What that means is that spring potential energy is always going to be positive, that even if your delta S is negative, once you square it, that becomes a positive value. So please be careful about that. If your spring is sitting at the equilibrium length, that means that delta S is 0 and you have no stored energy in that system. So let's think about a scenario where we have a transformation of energy between kinetic and spring potential energy. In this case, our system is going to involve our box, which is moving, a frictionless surface, and then our spring and the wall that the other end of the spring is attached to. Initially, we have our box that is traveling to the right with some initial speed. Again, we're not worrying about friction. And you can see that this is a before and after diagram, which is the best type of diagram to do for energy scenarios. And so the after moment that we're considering is when the box is momentarily brought to a rest and it has compressed the spring in. And note that this is being given as a delta x, and so our initial length of the spring is our equilibrium length, so this compression is the distance from equilibrium. So initially we have kinetic energy, and keep in mind that our system energy is kinetic plus spring potential. We don't need to worry about gravitational potential energy since everything's happening at the same height. You could think about it, but it's not changing, nothing's happening with it. So our kinetic energy, initially, we would take that initial velocity, find its magnitude, which is the speed, and square it. Now at the end, at this point, the box is brought to rest. So our final kinetic energy is equal to 0. We then need to define our initial spring potential energy and our final spring potential energy, remembering that spring potential energy was given by 1/2 k delta x, in this case squared. Initially, our spring was sitting at equilibrium length, so its potential energy at that point was 0. Now our spring is compressed, so we would plug this value in to get the energy. So if what our goal is to find the initial speed, we now use the fact that energy is conserved in this situation since there is no external forces. Because of the isolated system, we say the change in system energy is 0. Our initial system energy equals our final system energy. So we can say that our initial kinetic plus our initial spring potential energy equals our final kinetic plus our final spring potential energy. Now we plug in these values. It's really important to not just start by setting things equal to one another, but as always, to start with a valid equation, which I've done here and gotten to the individual energies. We then use the value that we see for our initial kinetic energy, which contains the speed that we're trying to find. Our initial spring energy was 0, our final kinetic energy is 0, and our final spring potential energy is given by the spring constant and that compression. And so from this, we're able to then solve for the unknown initial speed based on the rest of the parameters being known. So that is how you would actually do a calculation like this using spring potential energy. Now we have more than one type of potential energy now. One is gravitational, another is spring. Please do use the subscripts to distinguish between the two anytime you have both of them. That's especially important. So we could talk about just the total amount of potential energy, either in the before or the after scenario, or we can talk about the change in potential energy, where that would mean the change in both of these added together. Now, where this is going to occur that you would have both is, for instance, if you think about a mass on a vertical spring. You have that spring force that is going up and down, depending on whether the spring is compressed or stretched, but you also have the gravitational force going down. So depending on how the vertical position is changing, you have a change in your potential energy and you have a change in your spring energy. You would also, as it's moving, have changes in your kinetic energy. So please be careful about noticing what types of energy you have and being very clear in your notation. In this class, in the first part of intro physics, we're not going to have other types of potential energy, but when you study electromagnetism, other types of potential energy are going to occur.